but I have to check the textbook. So in the next lecture or after the tea, I will confirm. Most likely this is the Cavendish relation. Now, so we have understood European scaling by virtue of the pattern model, but now comes her question. Obviously, I do not know the F's, so I have to extract them from experiment. But how the hell do I extract them from experiment if I don't know how many FIs are there? In principle, there can be many. In fact, we cannot entirely say unless we make another bold hypothesis. So we have to now go to the quark pattern model, that is identify the patterns with the quarks. Now, how many quarks does a proton have? 3, right? U, U, D. Now, if I make such a simple picture that the quark is made of if the patterns are basically 3 quarks, the whole idea will fail. Experiment cannot be fitted. You will soon see one example, most likely. Yes, most likely you will see one, not most likely, definitely you will see one example which will convince you that if you take only 3 valence quarks, it fails. Doesn't work. Therefore, we have to borrow ideas from atomic physics. What is atomic physics? Suppose you consider a chemical reaction. Which participates in chemical reaction? It means 2 atoms, the valence electrons. So there are lots of electrons inside an atom, out of which there are a few valence electrons, that is in the outermost orbit, which participates in chemical reaction. So Gelman's idea will be generalized by the following sense, that there are 3 valence quarks inside the proton. But then there are large number of QQ bar pairs, and these are called C. Remember, if you add QQ bar, we will get a better picture towards the end of this lecture. But if you add QQ bar pairs, the quantum number of the proton does not change, because if you have a QQ bar, it is electrically neutral, all other quantum numbers will cancel each other, and therefore this does not harm anything. So let us say that in addition to 3 valence quarks, there are a large number of which we call the C quarks. Then in the quark parton model, I will write when you write the U quarks, now I will write this density function F as quark density functions, and I will write it in the following way: 2/3 square, because here we are following Gelman that the quarks are charged 2/3, and then UPX bar Px. So UPX is that a U-type quark in a proton carries X fraction of the proton momentum. That probability is UPX. And this probability U bar Px is that a U anti-quark carries X fraction of the proton momentum. Then I will write 1/3 square meaning is the same, except that we are now talking about D quarks, and D quark has a charge -1/3. What about the neutron? Any question? Yes.
So how can you get the values 2/3, 1/3, 1/3?
Oh, that is the quark model of the proton. Right? Rather, quark model of the hadrons. That is, the quarks must carry charge 2/3 minus 1/3 minus 1/3. Okay, if you add 2, then it is 4/3. So proton has 2 up quarks. So it is 4/3 and 1 down minus 1/3. So this is Gelman's idea. So I will get a very similar formula, except that so this is for E neutron scattering, except that in this formula I will change the level. That is, the proton level will be replaced by neutron, which means that UNX will be the probability that a U quark in a neutron carries X fraction of the neutron momentum. They need not be the same. However, there is one important thing. Yes?
So here you are considering UUT, right?
No. Plus any
Plus
number
the
of
C
U
quark.
bar pair.
Right. So that number.
So this is most general.
Right.
There are UU bars. Some of the U's are balanced, some of the U's are C. All U bars are C because there is no valence U bar in a proton. You understand this?
Right.
So this is fully general. There is no assumption up to this point. Yes? A stands for the stage. Normally in proton there is no S quark. We will say there is no S valence quark. Both S and S bar comes from the C. things will become a little clear towards the end of this lecture. So we replace T by N. Then we use isospin relation. What is the isospin relation? Those who do not understand, forget it. Take these as assumptions. Those of you who know isospin, you know that proton is isospin upstate of the nucleon and D is the downstate. So if I make a rotation in the isospin space, the proton becomes neutron. According to Gell-Mann's idea, U and D also belong to an isospin doublet. Therefore, if I rotate similarly U and D quark, we convert a proton into a neutron. Therefore, we use the isospin relation, namely that UP x is equal to dnx, and in order to avoid writing these indices again and again, I will write this as ux. Remember, ux means the density of U quarks inside a proton. Okay? And dn means, so what it means is the density of a U quark inside the proton is the same as the density of D quark inside the proton. So if you assume valence dominance, this is obvious, because there are two D's inside the neutron and two U's inside the proton. Therefore, roughly speaking, if the valence force dominates, then the density of a U quark inside a proton should be the same as the density of a. But those of you who do not know isospin, just take this as an assumption. If it works experimentally, fine. Furthermore, we assume dp inside the proton is same as the density of U quarks inside the neutron, and we give this a common. Third one is this will also become less fuzzy towards the end of this lecture. We assume what is called a SU3 symmetric C, which in simple terms means U. Okay, now before that, I am sorry. Before that, I should have written it in intermediate state, and that is, now which one to erase? I think I can erase this. So as I told at the beginning, total density of the U quark is the density of the valence quarks plus the density of the C quarks. And similarly for D of x is D of Vx plus D of Ck. And finally I make this assumption, that is SU3 symmetric C. And this in simple terms simply means that now you can go back to this formula and substitute. For example, for UPX, you will simply substitute UX. For UNX, you will simply substitute EPX, and so on and so forth. So you can write down explicitly both F2EP and also you can write down F2EN, that is for the electron-neutron scattering. And as I said, these F's can be extracted from data, so this is measurable.